Here we are given a list of molecules, and what we are explicitly looking for is a molecule that has a zero dipole moment. Nowhere in here does it say that it's just a bond. We're looking for an overall dipole moment of a molecule. So there's a couple things that we want to look for that will make our lives a lot easier. So when we refer to this dipole moment, what we're really looking at is something that is considered to be polar. So this uneven distribution of electronegativity. The way that I tell students to think about dipole moments in polar molecules is if I have some element X attached to itself, chances are high that the pair of electrons that they're sharing is smack dab in the middle. However, if there was another element like at Y, maybe the electrons will be closer to the X than the Y. This is an uneven distribution because maybe the electronegativities are slightly different. And this is why that arrow that you see, that polar arrow, comes into play, because the arrowhead always points to where the electrons are favored. The other way that I think about it is if you look at the tail kind of looks like a positive sign. So it shows you that arrowhead is the more negative side, the tail is the more positive side. So what we're looking for are molecules, so we're looking for just how many and the way in which all of these dipole moment arrows are associated. But if in order for you to have a polar molecule, there are two giveaways that make our lives a lot easier. Number one is that whether or not the central atom has any lone electron pairs. Now, this is not a guarantee. If you go to more expanded octets, you'll notice that just because you have two lone pairs might not necessarily mean you have a polar molecule. But if you don't have an expanded octet, chances are good that a central atom with one lone pair or two lone pairs of electrons will be a polar molecule. The other thing that we're looking for are going to be terminal atoms that are different. Because with different atoms, you'll have different electronegativity values. So any type of disparity in terminal atom versus the central atom, that's good for us. But here's the wonderful thing about this list of 5. Not everything is a complicated molecule. Our first two are CS2 and SO2, but that's great. Well, it's not really great because those are 3 elements, but 3 atoms. But take a look at HCl. That's 2 elements. That's 1 hydrogen attached to 1 chlorine. Since they're not the same, as I just showed you right above my head here, since they're different, there's going to be a polar moment, a dipole moment between the two. So HCl is a no. This one will have a non-zero dipole moment, so that can't be our answer. Just like how carbon monoxide will also not be a zero dipole moment, because it's not oxygen, they're not the same element. Carbon and oxygen will have a disparity on where that pair of electrons will be located. It definitely won't be directly in the center. So anything where I have a molecule that's just 2 atoms and they're not the same is going to be a dipole moment. So now we have 3 compounds or 3 molecules that have more than 2 atoms. We're going to need to draw these to determine whether or not I have a polar molecule or not. So the first thing I'm going to do is I'm going to draw my CS2 first, and let me just go ahead and continually mark out what I'm not using. So according to my periodic table, I will have carbon that has 4 valence electrons, and sulfur will have 6 valence electrons. Now, I'm only going to multiply the carbon by 1 because I only have 1 carbon in there, and I have 2 sulfurs, so I have 12 electrons to work with. So a grand total of 16 electrons to work with a carbon in the middle. Because if I go to my periodic table and I see my carbon and I see my sulfur, my electronegativity at my carbon is less than the electronegativity I have for my sulfur. So since I have that electronegativity difference, I know what my central atom is going to be. I'm just erasing because I will be using this a lot. So carbon in the center, sulfur, sulfur. I just used 2 bonds, which is 4 electrons in play, meaning I have 12 electrons to work with, and those are all going to go to my surrounding sulfurs. 2, 4, 6, 8, 10, 12. And if you're asking why, remember, whenever you're drawing the Lewis structures, you do your bonds to your central atom first, and then you fill up all the terminal atom electrons before you touch the center atom. But all 12 of my electrons have been used. So if I was to calculate my formal charge, the formal charge of my sulfur will be 6 minus a single bond plus 6 non-bonded electrons, which is a -1, while the formal charge on my carbon is 4 minus 2 single bonds and no non-bonded electrons, which is a +2. So since this is a negative and this is a negative, this is a positive and positive. The reason I'm putting those positives there is because I'm going to make double bonds. And any time that you make a double bond from a pair of electrons, it cancels out one negative charge with one positive charge. So I make two double bonds, my negative and positives cancel, leaving me with a pretty uniform structure of a carbon with a sulfur on the left and a sulfur on the right. So even though carbon-sulfur bond will be a polar bond, notice that the arrow is in two different directions. I have an arrow pointing towards the sulfur and an arrow pointing towards the sulfur. But here's the key thing to remember about a polar molecule. You need to have a negative end and a positive end. It's kind of like what you need is one arrow, one of these dipole arrows for the entire molecule. Notice here for these arrows that I have a positive charge in my center and I have a negative charge at both of my ends. So this is not a polar molecule because in order for this to be a polar molecule, one sulfur needs to be a positive side and the other sulfur needs to be a negative. There needs to be a positive end and a negative end. There's no positive or negative ends in here. It's just negative outside, positive inside. So CS2 actually will have a zero dipole moment. So the answer for this is going to be CS2. However, because this is an instructional video and I want you to really understand what's going on here, I'm going to continue on with our SO2, just to show you why SO2 is not one of our answers. So SO2, sulfur and oxygen is right on top of each other in the periodic table, and I just showed you that sulfur has 6 valence electrons. So I have sulfur, which is 6. I have oxygen, which is also 6, multiplied that by 2. And I have 12 plus 6, which is 18 valence electrons to work with. Now we need to look at our periodic table to determine what our central atom is. Oxygen sits on top of sulfur. So the electronegativity for my sulfur is less than the electronegativity for my oxygen, which means that sulfur is my central atom. So sulfur in the middle, oxygen, oxygen, bam, bam. 4 electrons have been used, leaving me with 14 electrons remaining. So I fill up my terminal oxygens first, and wouldn't you know it, I only use 12. Meaning I have 2 electrons left over, so I'll put those on the sulfur. I don't have to go any further from here because I will have that lone pair of electrons on that sulfur. Because in order for me to balance out my distribution of formal charges, they're going to be using the electrons from my oxygen. Remember, oxygens cannot expand. So I cannot take these lone pairs and I can't put them here, nor can I put them here, because that would mean that one of those oxygens expands. So I'll be left with that lone pair on the sulfur regardless of what happens, meaning that I will have a polar molecule because my central atom has a lone pair of electrons on it. I don't know why I wrote that as an asterisk. I meant to write that as an X, meaning nope. So SO2, not an option, and let's go to the last one, which was the dichlorine oxide. Nope, 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 yep. So here we go. Chlorine is going to be a halogen, so I have 7 electrons for every halogen. Multiply that by 2 because of my subscript of 2. 14 electrons. My oxygen is 6, and multiply that by 1, so I have 6 electrons to work with. So I have a grand total of 20 electrons. Now this is that rarest instance where my oxygen is going to be the central atom because oxygen's electronegativity is less than the electronegativity of chlorine. Because if you look at the periodic table, chlorine is a halogen right here in group 7, and those are very electronegative. So chlorine's electronegativity is going to be greater than that of oxygen. So oxygen in the middle, chlorine, I've just used up 4 electrons, so minus 4 is 16 electrons remaining. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons have been used. 4 electrons remaining. Those 4 are going to go on the oxygen. And there you have it. I have 2 lone pairs of electrons on my oxygen, which means I do, in fact, have a polar molecule. So, Just to recap why CS2 is our answer. CS2 is our answer because when you first set up all of your initial Lewis structure, you have the single bond with the carbon and the sulfur. You make the double bonds, and even though the carbon-sulfur bond is going to be polar, you have the same exact polar bond on the left-hand side as you do on the right-hand side. So those arrows essentially cancel each other out, leaving you with an overall net zero dipole moment of the molecule. It's very important that you know you're dealing with the molecule and not the actual bond itself.